It should be live at some stage. Should be live. Are we live? Are we live? Okay, we should be live by now. There's a bit of a delay. Okay, so as you know, we are developing this website called BioniChaos.com. There is a bunch of tools. Go check them out. They're around neurology, cardiovascular, biomedical imaging, vision, hearing. Go check all the tools and provide your feedback. And we will be jumping into a few things. Oh, forgot the LinkedIn stream. Forgot to start the LinkedIn stream. So it should be on now. Then it's actually streaming to the thing. It's not coming up. Okay, now it's okay. Now we should be properly live. So we have emergent behavior simulators. We have obviously game of life. It's like a special version of it. And we have brain seizure simulators, and that's the ones, unless there is a human who wants to chat. Any humans? No. We'll try later. Get the professional podcasters reviewing this. So talking brain seizure simulation. Yeah, we'll talk about this education tool and other resources. Which one should we do first? Should be able to hear me all right. Let me know if you can hear me okay. So there is a human in the loop while the bots are playing and the simulation is going. There is a human in the loop. So if you have any questions, go for it. Hey, go for the chat and smash that like button.
Okay, let's unpack this. The human brain. I mean, it's the ultimate black box, isn't it? A whole universe of electrical storms, memories, consciousness, and governed by principles we're really only just starting to get a handle on.
Absolutely. It's incredibly complex.
Yeah, like imagine trying to predict something as simple as, well, a specific thought someone might have.
Yeah.
It's almost unimaginable, that challenge. Yet we're, relentlessly trying to unlock its secrets. We're using everything from really cutting-edge AI to, well, sometimes surprisingly low-tech simulations.
Right.
But what happens when these tools we build to understand the brain actually start to redefine what it means to be human?
Yeah.
That's what we're diving into today, this fascinating, complex, and yet sometimes unsettling journey. We're focusing on epilepsy specifically, and the incredible ways technology is trying to, quote, demystify the brain 1 millisecond at a time.
It's a great focus point.
So our mission here in this deep dive is to pull out the key nuggets from the sources you've provided, understand how we're simulating, treating, maybe even rewiring the brain.
And then face those big, sometimes quite ironic questions that all this progress brings up.
And what's truly fascinating here, I think, is just how far we've come. From basic statistics to machines that learn from their own mistakes at unbelievable speed.
Yeah.
And this evolution has profound implications, especially for conditions like epilepsy, where predictability, well, that's often the biggest hurdle.
Absolutely. So let's start there. With understanding these electrical storms, some brains experience epilepsy. Basically, it's a central nervous system disorder.
Right. Characterized by hyperactivity, an imbalance between excitation and inhibition.
Exactly. Imagine your brain like a bustling city, right? Millions of signals like cars moving on roads. Excitation is the green lights go, pathways open. Inhibition, that's the red lights, the traffic cops, making sure things stop when they should, preventing pileups, keeping flow.
And necessary control. Right. But in epilepsy, those red lights, the healthy inhibitory bits, they're damaged or just not working right. You get this uncontrolled cascade, this traffic jam of electrical activity.
Which the sources describe as electrical storms, sometimes even hurricanes. It's a powerful analogy.
It really is. And these aren't rare events, are they?
No, not at all. The scale is significant. Back in 2015, about 3.4 million people in the U.S., so 1.2% of the population, were living with epilepsy.
Wow.
And what might truly surprise you is the lifetime risk of having at least one seizure. It's about 4%, roughly 1 in 25 people.
1 in 25. That's much more common than I think most people realize.
Precisely. And that unpredictability is why it's such a persistent challenge, especially because a third of cases become drug resistant.
A third.
Yeah. This is often called refractory epilepsy. It's so widespread, so tricky to treat, that new medications, they're often benchmarked just for seizure reduction, not necessarily complete freedom from seizures.
So just making the storms less severe, not stopping them entirely.
In many cases, yes. And for these complex, drug-resistant situations, doctors often need more invasive methods, things like intracranial EEG or IEG.
Okay.
That helps them pinpoint exactly where the seizures are starting. It provides, as one source puts it, unprecedented time and spatial resolutions. We're talking milliseconds and millimeters.
So an incredibly detailed map of the storm's origin.
Exactly, almost microscopic, seeing the specific neurons that are misfiring.
Okay, so here's where the plot thickens, right? Because to handle that level of detail, that complexity, we're bringing in the big guns. Artificial intelligence.
AI.
And the whole concept, AI and machine learning, it arguably sparked after World War II, didn't it? With code breaking, things like Enigma, the bomb machine.
Word computation, yeah.
By 1951, you had the Ferranti Mark I mastering checkers. It's just wild to think about that trajectory, from mechanical calculators to this.
It really is. And AI, at its core, it's about creating intelligent machines, using sophisticated programming, computational methods.
Like superpowered pattern recognition.
You could say that. Mathematical functions on steroids, maybe? Capable of spotting subtle patterns, predicting outcomes way faster than any human could.
Okay.
And then there's deep learning. That's a more advanced type of AI.
Right, that mimics the brain itself.
In a way, yes. It uses these hierarchical neural networks. And instead of being programmed for every single possibility, it learns from its mistakes. It refines its understanding iteratively.
How fast does it learn?
At the speed of electrical circuits, as one source puts it. So incredibly quickly.
And it's achieved some pretty impressive things already.
Definitely.
Famously beating the world champion in Go, that incredibly complex game.
Right.
But more importantly, for diagnosing some specific diseases, it's apparently already matching experienced physicians, medium or even senior level.
Yes. That's where the real impact lies. It's not just games.
It's life-changing stuff.
And that's exactly where the brain-computer interface, the BCI, comes for play.
Okay, BCI. Define that for us quickly.
So a BCI is essentially a device that reads brain activity and translates it, turns it into a message or a command for a computer.
Got it.
When you combine that with AI, you get this incredibly detailed picture of brain activity. It's utterly transformative for epilepsy care.
How so? Give us some examples.
Well, current examples include things like responsive neurostimulation, RNS systems. NeuroPace is one brand.
Okay.
These aren't just diagnostic, they're devices implanted in the brain. They can detect a seizure just as it's starting.
Wow.
And deliver tiny electrical currents within seconds to stop it, or at least lessen it significantly.
Real-time intervention, like an internal firefighter for those electrical storms.
Exactly, an internal traffic cop, maybe.
Yeah.
Another amazing example is gamma mapping.
Gamma mapping.
Yeah. This used to be a really laborious process. It could take days. You're trying to map out critical brain areas, language, motor control before surgery so you don't damage them.
Right. Crucial but slow.
Very slow. Now, with AI and BCI working together, they can get comprehensive results in under 30 minutes.
Under 30 minutes. Down from days. That's revolutionary for patient care, surely.
It absolutely is. And think about the data involved. That intracranial EEG we mentioned. It generates data at a rate of 43 books per second.
43 books every second.
Yep. Enough info to fill a small library constantly. It's mind-boggling.
I can't even picture that amount of data.
Exactly. And it's far beyond what any single neurologist could possibly process manually. But it's perfect for AI.
Right. AI thrives on that scale.
Precisely. It allows the AI to pinpoint seizure origins, identify subtle patterns with incredible accuracy. This leads to much better treatment plans, often even before resorting to invasive surgery.
So stepping back a bit,
Yeah.
what does this mean for medicine more broadly? One of our sources, a doctor, seems convinced AI should just take over a lot of these time-consuming tasks.
Well, it's fascinating, isn't it? AI excels at picking up on all those subtle, weak features, things often called medical art.
The intuitive stuff.
Exactly. The patterns a really experienced doctor might sense, but can't easily quantify or explain. AI can analyze those across vast data sets.
Okay.
And this could improve almost everything, from surgery in difficult environments like war zones to basic diagnoses in underserved areas. It could potentially democratize expertise.
Democratize expertise and, as the source puts it, automate drudgery.
Chuckle slightly. Yes, automate drudgery.
Which sounds great for freeing up doctors' time.
Yeah.
But when you talk about medical art or those human aspects,
Yeah.
does automating the analysis risk losing something? Could healthcare become too efficient, maybe lose some of that human connection?
That is a critical question. It's the balance we need to find. The hope, I think, is that it frees up clinicians to actually engage more deeply with patients. On an emotional level, understanding their lives, personalizing care.
Instead of being buried in data.
Right, instead of administrative tasks or sifting through terabytes of EEG data. But ensuring technology serves that human connection rather than replacing it where it's vital. That's the ongoing challenge. It requires conscious effort and dialogue.
It definitely does. Okay, so on one hand, we've got AI churning through terabytes, pushing the absolute limits of neural understanding. And then, and this is where the irony kicks in beautifully, we have these incredibly ingenious, surprisingly effective, and honestly quite amusing low-tech ways to simulate seizures.
It's quite the contrast, but it speaks to human ingenuity, doesn't it, across the whole spectrum?
It really does. So tell us about these low-tech simulations.
Well, there are general educational tools first.
Right.
Like the brain seizure simulation. It visualizes neurons as little particles changing color, moving, showing localization, intensity, the different phases.
A simplified visual model for learning.
Exactly. An artistic interpretation, you might say. Not AI, but still very effective for teaching the basic concepts.
And then it gets more hands-on, more immersive.
It does, especially using virtual reality, VR. There's compelling neuroscience research showing our brains treat VR experiences almost like real life.
Really? So what you do in VR predicts how you'd act in reality?
To a strong degree, yes. It makes VR an incredibly powerful training tool. One study, for instance, looked at a VR program for parents, VR ESMEP, it was called.
Okay.
It successfully boosted parents' knowledge and skills in managing their child's seizures. That's huge.
Wow, empowering parents directly.
Exactly. And for nursing students, simulation training didn't just improve knowledge and skills, it also improved their positive attitudes towards epilepsy.
That's fascinating. Affecting empathy and confidence, not just technical skill.
Right.
Ties back to that human connection we were talking about.
Precisely. It impacts the whole approach to care.
Okay, but now, let's get to maybe the most wonderfully absurd example. The super low-cost seizure simulation. For mannequins.
Ah, yes. The mannequin challenge.
Right, trying to train medical staff, maybe in places with limited resources.
Yeah.
In the first attempts, apparently, they just involved shaking the mannequin's head.
Chuckles, which, as the source notes, was quite distracting. And probably not very realistic.
You think? So then came the, let's call it, innovative approach.
Indeed. What did they do?
Okay, get this. They put mobile phones, set to vibrate, under the mannequin's upper arms, hidden in the sleeves.
For tactile feedback, simulating tremors.
Exactly. Tactile fidelity via phone buzz.
Yeah.
And for the legs, they used unwaxed sewing linen thread.
Thread.
Looped between the ankles and manually pulled by a facilitator standing nearby.
Laughs.
Yeah.
They were literally pulling strings to simulate a seizure.
Literally pulling strings.
Yeah.
It's genius in its sheer resourcefulness, but also just brilliantly comical.
It really highlights that need for functional fidelity, doesn't it? Even if you can't get perfect physical realism, you create enough cues for the brain to engage and learn.
And apparently it worked. Experts admitted the vibration frequency wasn't quite right, obviously, but the participants, they found it realistic, emotionally engaging even. What does that tell you? Because for me, it says something about our brain's ability to just suspend disbelief, to learn even when we know it's just a phone and some thread.
That's a fantastic point. It speaks volumes about our capacity for immersion, for learning from models that are functionally useful, even if imperfect. Maybe perfect physical fidelity isn't always the most crucial thing.
Maybe not. It makes you wonder, doesn't it? How much can we learn from simple models if they capture the core function? It's a reminder that, sometimes the simplest hacks are surprisingly effective.
Tapping into fundamental learning mechanisms.
Yeah. Of course, this low-tech marvel wasn't perfect. The source notes, the seizure activity was limited to the limbs only.
Right.
And clenching of teeth, tongue bite, and creation of a difficult airway could also be incorporated.
Chuckles. Okay, imagining how they'd simulate a tongue bite with thread and a phone.
Like,
That's
something else, isn't it?
Yeah.
The dedication is admirable, if
Right.
slightly terrifying.
Indeed.
Well,
Admirable and maybe a little unsettling. But this brings us squarely to the more serious side of things.
right. Because as we get better at this understanding, simulating, maybe even manipulating the brain with high-tech AI or low-tech string.
We hit some massive ethical walls.
Exactly. It's not just about treating disease anymore, is it? There's this looming possibility of enhancing normal brains.
Boosting memory, intelligence, creativity.
Yeah.
Going beyond the natural baseline.
And that opens a huge can of worms. Who gets access? How do you regulate it? When does enhancement become, I don't know, brain doping, creating unfair advantages?
These aren't just abstract philosophical points. They force us to confront this tension between healing and enhancing. And the truth is, maybe we're not fully prepared as a society to answer them.
It feels like the tech is outpacing the ethical frameworks.
Often, yes. Take gene editing, for example. Hugely promising for diseases like Huntington's. But there are risks, unknown side effects maybe decades later, immune reactions. And even with noble intentions, there's always the potential for, well, alternate use, misuse, things the inventors never imagined.
Like what? How could brain augmentation be misused?
Well, think about memory enhancement. You could see military applications, right? Boosting soldiers' cognitive capabilities, creating super soldiers. It raises profound...
Definitely.
And we've already seen gene editing arguably go too far. Remember in 2018, the Chinese researcher who announced he'd used CRISPR to create the first gene-edited babies?
Vaguely, yes. To make them HIV resistant.
Purportedly, yes.
Yep.
But with potential serious off-target effects, maybe even life-shortening mutations, it was a huge controversy, a stark reminder of this ethical tightrope. Good intentions maybe, but potentially grave unintended consequences.
That's chilling. And what about the impact on our sense of self, our identity?
That's another huge area. Techniques are emerging, using light to control neurons, optogenetics, or transcranial magnetic stimulation, PMS. These can temporarily alter brain function.
Change how the brain works, even for a short time.
Exactly. And the deeper we go, the more these interventions could potentially tweak someone's personality, their core identity.
So, who are you if your brain is being artificially altered?
Precisely. How much responsibility do you bear for actions taken under that influence? What's the threshold? When does manipulation cross a line where your brain isn't really yours in the same way? Is it still normal?
These are fundamental questions about personhood.
They are, and it highlights how research doesn't happen in a vacuum. It's tied to societal values, to policy. Researchers pushing boundaries know, or should know, there are potential downsides alongside the benefits. It's a constant dance. Innovation versus responsibility.
A dizzying dance, it sounds like.
Right.
We've really covered some ground today. From understanding epilepsy's complex storms to AI and BCIs crunching data at impossible speeds, and even appreciating the, let's say, unique ingenuity of the phone and string simulation.
Chuckles softly, quite the range.
We've seen tech automating drudgery, maybe even rewiring brains for the better, sometimes before surgery is even needed.
Yeah.
It really is a world where sci-fi is becoming medical fact, forcing us to rethink everything.
It is. And the journey for epilepsy treatment, it's come so far from when it was just called falling sickness. AI's integration into medicine. It's going to be transformative, there's no doubt. Advancing knowledge, democratizing expertise, allocating resources more effectively. The real question isn't if, it's when. And, maybe, how many generations until we reach what seems like the next logical, if perhaps slightly unnerving, step.
Which is?
Human-machine hybrids. Using technology seamlessly as part of ourselves, maybe even using it to overcome some of our less helpful encoded evolutionary traits.
Human-machine hybrids, mitigating our evolutionary baggage. Wow. Okay, so as we think about that future, where our brains are augmented, maybe subtly redefined by the tech we create, what does that make us? Are we just biological machines with better upgrades? Or something fundamentally different? That's definitely something to mull over until our next deep dive.
Yeah, there is a human in the loop, by the way, if you were wondering. If you have any questions, go for it. Should be live both on YouTube and LinkedIn for your convenience. As you know, we're developing this website called BioniChaos.com. It has tools around neurology, cardio, imaging, biomedical imaging, vision, hearing, EMG. So a lot of simulations, modeling, AI, obviously, as well as some game signal processing. So go check it out. Let us know what you think. Don't forget to smash that like button. Subscribe, unsubscribe. You know what you have to do. Yeah, okay, let's try something else. This synthetic PPG waveform visualizer. Do a short overview of the page.
Welcome back to the deep dive. You know, sometimes you look at your fitness tracker, see those numbers, heart rate, SFBO2, and you kind of wonder what's really going on inside. It feels a bit abstract, doesn't it? So today we're going to unpack something called Pulse Vision. It's this web application designed to take those abstract signals, specifically photoplethysmogram or PPG waveforms, and make them visual.
Yeah, and the sources we looked at give a really good sense of what pulse vision is. It's very interactive, and they even hint at some pretty interesting future developments.
Exactly. It's a neat way technology can make complex body stuff, well, easier to grasp.
Definitely more accessible.
Our mission today, then, is to see how this tool lets you actually see how different health things change this key signal. It's like a shortcut to understanding those vital signs better. So, okay, let's just jump right in. What is pulse vision, fundamentally, and why is it helpful?
Well, at its heart, pulse vision is about visualizing synthetic PPG signals. These are the kinds of signals used everywhere now to track things like heart rate and blood oxygen. What makes pulse vision neat is how interactive it is. It's really built for learning. You can tweak things and see the signal change instantly.
Right, that interactive part sounds key. So you're not just seeing a static picture, you can actually, like, play with it.
Exactly. You're experimenting, not just observing. There are these sliders you see. For example, the heart rate slider BPM, beats per minute. You slide it up, the waves on the screen get closer together, faster. Slide it down, they spread out slower. You literally see the heart rate change.
Okay, that makes sense. What about other things like oxygen levels?
Yep, there's an oxygen saturation slider too. This one changes the amplitude, basically, the height of the waveform. So higher oxygen might show up as a taller, stronger looking pulse wave. Lower oxygen, The wave gets smaller, less pronounced. It gives you a visual feel for it.
And I remember reading about other controls too, something about sharpness and the dichrotic notch. What's that?
Ah, good catch. Yeah, the dichrotic notch is that little secondary bump you often see after the main peak in the waveform. Its shape, its prominence, can tell you things about, say, how stiff or flexible your arteries might be. Pulse vision lets you adjust how noticeable that notch is. And you're right, there's more. You can change the overall waveform sharpness, make the peaks pointy or rounded. Plus, you can add noise level. This makes the signal look messier, more irregular, kind of like what you'd get from a sensor in, a less than perfect real-world situation.
I see. So it's not just numbers becoming a picture. It's about getting a feel for how all these things connect dynamically, like how one change affects the whole signal.
That's exactly it. It helps build intuition. You see how even a small tweak ripples through visually. It connects the dots in a way numbers alone might not.
Okay, that makes a lot of sense for learning. So given what it can do now, what's next? The sources mentioned some potential future stuff.
Oh yeah, the future possibilities are quite exciting. They talked about adding more controls. Imagine sliders for maybe respiratory rate, or even trying to simulate aspects of blood pressure visually.
Wow, that would make it even more comprehensive.
Definitely. And another big idea is simulating problems, like abnormalities. Think about being able to show what an arrhythmia looks like on the waveform, or having presets for conditions like tachycardia, that's a fast heart rate, or bradycardia, a slow one, or even hypoxia, low oxygen.
That sounds incredibly useful for, say, students or healthcare trainees.
Absolutely. And for the data geeks, there's talk of maybe calculating metrics like heart rate variability, HRV, right there in the tool. Plus, the idea of being able to save or export the waveforms you generate. That opens up possibilities for people to track things over time, share data, maybe even use it for personal projects or research.
So wrapping this up, what's the big takeaway here? It feels like tools like pulse vision are really shifting how we can understand our bodies.
I think so. They make complex data feel more tangible, understandable. It moves us beyond just seeing numbers to actually visualizing what's happening inside.
Brings clarity, right?
Exactly. And it raises a really interesting question for everyone listening. How could tools like this, these interactive visualizations, change how you look at your own health data? Could it help you move past just tracking numbers to gaining, real insight, deeper understanding?
Something to think about, the power of seeing your body's signals come alive. We hope this deep dive sparked some thoughts. Join us next time for another exploration.
Okay, so that was obviously Notebook LM. I don't think I can do any better. Well, unless another human joins in or something. If you have any questions, yes, there is a human in the loop. Otherwise, we'll keep using the robots. So what shall we jump into next? Or should we do some development? Yeah, let's do something more fun real quick. We have this like emergent behavior tools. So we have the void blocking animation simulation and the game of life. We actually want to add some more.
Welcome to the Deep Dive. We're the show that takes that pile of source material you send us, digs through it like treasure hunters, and pulls out the key insights so you don't drown in information. And today, we're plunging into something pretty fascinating, pops up everywhere, really, from weird biological evolution to the absolute latest in AI. Emergent behavior. You've given us quite the stack this time. Articles, Reddit threads, academic papers, covering machine learning, biology, simulation theory. It's a lot. So our mission today, let's unpack what emergent behavior actually is. Where does it show up in these surprising, sometimes frankly unsettling ways? And why should you care? Why is understanding it so crucial? Get ready. It's going to get a bit mind-bending. Probably some dark humor along the way. And maybe, just maybe, you'll question how much control we really have over, well, anything complex. Okay, so let's just dive right in. Emergent behavior. We hear this term thrown around constantly, right? Especially with AI. But what are we actually talking about here?
Right. Well, at its core, it's describing situations where, the big picture, the system's overall behavior or properties, you just can't easily predict it or figure it out logically just by looking at the little pieces, the individual components. Think of it like the whole is more than the sum of its parts, or maybe just very, very different. Our sources, they actually point out two main flavors. There's strong emergence, where the properties literally cannot be logically figured out from the parts, like maybe ever. And then there's weak emergence. This is more about unexpected consequences that do follow from the rules governing the parts, but maybe in a super complicated way we didn't foresee. And for actually doing science, looking at this stuff, the sources suggest weak emergence is, well, a more useful concept. It means there's still a chain of cause and effect, maybe incredibly tangled.
Okay, so it's not just a buzzword. It's about genuine surprise. You set up simple rules, maybe super simple, but what comes out the other end can be unbelievably complex, like Conway's Game of Life, right? That came up in the sources. Really basic rules for these little cells on a grid: birth, death, survival. But then you get these patterns that look like they're alive, moving, evolving, completely unpredictable just from knowing those three rules. It's kind of mesmerizing, actually.
Exactly. That's a classic example. And it shows how our intuition fails us, right? We think linearly, A plus B equals C. But in these systems, A influences B, B influences C, and then C loops back and messes with A in a way you never planned. The interactions just explode combinatorially. Your brain can't track it all. The system acts like one thing, with properties none of the little bits have on their own. It's a different kind of complex.
Right. A tangled complexity. Okay, and this is where it gets really interesting, and maybe a bit dark, judging by our sources. This isn't just theory. It happens in some properly weird ways.
We've got some unforgettable examples here, starting with one from artificial life that's something.
Oh yeah, Polyworld. This was in a life simulation, artificial life, and there was this, let's call it an oversight in the programming, a bug. See, critters got an energy reward for eating another critter. Makes sense. But crucially, there was no energy cost for reproducing. Making new critters was free.
Uh-oh. I think I see where this is going.
You probably do. The researchers call them indolent cannibals.
Indolent cannibals, okay.
These digital things, they basically stopped moving much. Why bother? Their main emergent strategy became reproduce as fast as possible and then eat your own children for energy.
Wow, okay. That is bleak. But also perfectly logical given those skewed rules. Exactly. Grim, yes. But a totally rational, emergent behavior within that specific, flawed digital ecosystem, you can almost picture the programmer just staring at the screen going, what have I done?
Right. Like, you design this complex system maybe hoping for cooperation or something interesting, and they just figure out, hey, infinite free food source if we just eat the kids. It's almost a dark comedy sketch. It's pretty unsettling, though, if simple rules can lead there. What about the vastly more complex systems we're building now, like AI? Are we just setting ourselves up for weirder stuff? Like, the sources mentioned emergent machine sarcasm. Is the AI learning to be genuinely smarky?
Well, that's the million-dollar question, isn't it? That Reddit discussion about machine sarcasm, it really hits on a core debate in AI right now. Is the AI truly being sarcastic, understanding the nuance, the intent? Or is it just gotten incredibly good at mimicking sarcastic patterns it found in its vast training data, but doing it in a way we didn't explicitly program or necessarily expect?
Right.
The ML community is kind of split. Some argue maybe nothing a neural net does is truly emergent in that strong sense. It's just getting better at encoding concepts, finding correlations as you give it more data and more parameters. So maybe it's not developing a personality, just becoming a scarily accurate mirror. It looks like sarcasm, feels like sarcasm, but is it? That's the tricky part.
Okay, so maybe not self-aware comedians just yet, but
Yeah.
still eerily good mimics. It's not just digital critters or code, though, is it? This happens inside us. Our biology is full of this stuff.
Oh, absolutely. Biological systems are maybe the ultimate example of emergence. It's everywhere. Think about cells, like human dermal fibroblast skin cells. The sources mention how they can exhibit collective migration. They don't just move randomly when they're in a group, they coordinate. move together. That's emergence.
So they behave differently in a crowd.
Exactly. It's crucial for things like wound healing. And the sources even break it down further. They talk about primary emergence, where it's a direct result of an existing cell property, just amplified by the group, and secondary emergence, which is even more interesting. That's where the cells actually sort of evolve a new behavior because of the environment, like how dense the cell population is locally. The rules themselves can change based on interaction.
Wow. So my own cells might be improvising based on who's around them. That's kind of amazing.
It is, and it goes deeper. Think about the signaling networks inside our cells, inside our bodies. These incredibly complex pathways, involving molecules like PKC, MAPK, KMKII, KMP. These networks allow signals to last longer. They create feedback loops, positive and negative. They set specific thresholds for triggering a response. They can even split one signal into multiple different outputs. The sources say the intricacy here often defies analyses based on intuition. You just can't eyeball it and figure it out. It's too interconnected.
Okay, my brain hurts a little. So if systems can be this unpredictable, this complex, how on earth do we even begin to understand them, let alone control them? It feels like trying to predict the weather, but like inside every cell of your body simultaneously, or trying to manage an economy where everyone's an indolent cannibal.
Yeah, it's a massive challenge. And that's precisely why modeling and simulation becomes so incredibly important. Essential, really. So a system is just any collection of things interacting, right? And a model is our attempt to represent that system, usually simplified. When you can't just solve the equations directly, which with emergence, you often you simulate, you run the model, imitate how the system works over time, and see what happens. You estimate numerically. This is vital everywhere. Evaluating military tech, understanding those biological pathways, predicting how disease might spread. We build little digital worlds to try and get a handle on the real one.
Right. We build these mini universes, which sounds cool, but also like a ton of work just to maybe find out your simulated cells are also eating their young. But I guess it's better to find out in the simulation than, in reality, especially when the stakes are high, like in medicine.
Exactly. High stakes is the key. In healthcare, modeling isn't just nice to have, it's becoming fundamental. Our sources really emphasize the need for interpretable machine learning models there. Doctors, patients, regulators, they need to know why the AI is making a certain prediction, not just what the prediction is.
Ah, the black box problem.
Precisely.
Yeah.
You need to understand the global patterns the model learned, but also why it made this specific decision for this particular patient. If an AI suggests a radical treatment, you can't just trust it blindly. You need to interrogate its reasoning. The risk of some weird, unexpected emergent bias is too high. And another really interesting tool emerging, mentioned in the sources, is synthetic data.
Synthetic data, so fake data.
Kind of, yeah. It's artificially generated data. The goal is to make data that has the same statistical properties as real data, but critically, it doesn't contain any actual individual records. This helps tackle huge challenges, like protecting patient privacy. You can share and analyze the synthetic data more freely. Increasing access to data for research because privacy issues are lessened. And even just having realistic data to test healthcare software when real data is hard to get or too sensitive. Imagine training an AI doctor on millions of patients without ever touching real patient files.
Okay, that's clever. Creating a statistically accurate replica to sidestep privacy and access issues. It's like building a very elaborate ethical lie to find the truth.
It's a powerful approach. But like any powerful tool, it has its own complexities and risks. It's not a magic bullet. You have risks like data leakage, accidentally encoding real information into the fake data if you're not careful. The quality really depends heavily on the underlying statistical model you use to generate the imputation model. Get that wrong, and your fake data might lead you astray, and it might not perfectly capture all the nuances, especially those subtle emergent patterns in the original data. But still, it allows for huge advances, simulation studies, testing hypotheses, epidemiology, even in silico clinical trials.
In silico. So clinical trials run entirely inside a computer simulation.
Exactly. Using models potentially trained on synthetic data, testing new drugs or treatments virtually before you ever get near a real human. The potential to speed things up, make things safer. It's massive.
Okay, it feels like we're building these incredibly powerful digital tools, models, synthetic data sets, but there's still this underlying ghost of emergence. We're trying to predict the unpredictable. What are the big pitfalls here? Are we just getting better at being confidently wrong?
That's definitely a risk. Validation is absolutely key, and it's hard. Making sure your model actually reflects reality. The sources talk about different kinds of errors. We know about type 1, rejecting a good idea, and type 2, accepting a bad idea. But there's also the dreaded type 3 error. This one's insidious. It means you're solving the wrong problem. Your model might be accurate, precise even, but it's modeling the wrong aspects of the system or leaving crucial things out entirely.
So you can have a perfect answer to a completely irrelevant question. That's not reassuring, especially when we're talking about AI making big decisions.
It's a major headache for modelers, absolutely. And then there's another fundamental issue. Randomness, or rather pseudo-randomness. Most simulations need random numbers to work to simulate variability, chance events. But computers generate pseudo-random numbers using algorithms. They look random, but they're deterministic. And the sources mention this general distrust in the modeling community about the quality of many standard random number generators you find in software libraries. Some are just bad.
Bad randomness. How can randomness be bad?
Well, if the algorithm isn't good, it might produce patterns.
Right.
Or if you're running multiple simulations and you don't manage your random number streams correctly, you can get weird correlations. Your results might actually become negatively correlated when they shouldn't be, making your analysis less accurate, not more.
So even the chaos has to be high-quality chaos. It's like finding out the dice are loaded, but in your computer simulation, that's almost ironically emergent in itself.
It really is. It shows how deep the validation challenge goes. You have to check everything. And finally, the sources point out this kind of chicken-egg problem in research, especially between labs and simulations. Ideally, real-world lab experiments should inform how you design your simulations, and the results from your simulations should guide what experiments you do next in the lab. Each side needs the other to improve. It's this continuous loop, this back and forth, that helps us slowly, painstakingly, chip away at understanding these really complex emergent systems. It can be frustrating, but it's necessary.
Wow, okay. So that's our deep dive into emergent behavior. It really runs the gamut, doesn't it? From those charming, indolent cannibals in Polyworld
Let's not forget them.
to the incredibly complex dance happening inside our own bodies and into this really strange, fascinating, sometimes unnerving territory of AI. It's just this constant theme. Simple rules, simple parts interacting, and then bam, something totally unexpected, complex, and hard to predict pops out. Defies our basic intuition.
It really forces us to be humble, I think, to recognize the limits of just thinking things through linearly. And it highlights why these tools, modeling, simulation, careful validation, are so vital.
Yeah.
It teaches us that the really interesting stuff, the big leaps, the weird quirks, the dangers maybe,
Yeah.
they don't usually come from one single thing. They emerge from the interplay, the network, the system itself.
So maybe the takeaway is next time you're dealing with an AI or watching ants or even just thinking about how a crowd behaves, ask yourself, what are the simple rules here? And what unexpected things might be bubbling up just beneath the surface? How much is planned and how much is the system just doing its own possibly quite unsettling thing? Are we the architects or just the surprise observers? Thank you for joining us on this deep dive. Hope we've given you some surprising insights, maybe a chuckle or two amidst the existential dread. Always helps. And definitely some critical thinking to apply to all the complex emergent systems swirling around us.
There's a human in the loop, just if you were wondering. We're losing viewers on the stream like there's no tomorrow. I'd actually talk to the thing to keep it more focused. CEO is a bit all over the shop, but I'll try to bring it down to earth. And let's actually bring, let's do it quickly. So it's resulting, going towards genomics data. Let's see real quick, who do we like? Who do we like? Let's do Puck. We'll get them to chatting to one another. Okay, what's the agent is saying? Can you review it real quick? Make it fun.
Okay, it sounds like the agent is describing a super fancy 3D visualization of biomedical data. It's talking about glowing networks, a 3D model of a human brain with different colored streams of data flowing through it, like from genomics and brain scans. It's supposed to look really clean, futuristic, and scientifically accurate, making the complex data look visually amazing. Sounds like something out of a sci-fi movie.
Okay, how do we bring it back down to earth, something more realistic? How about turning time series data into a 2D visualization, into like a spectrogram?
Got it. How about we describe
Keep going.
Right. How about we describe a clear 2D spectrogram visualizing time series data? It would show frequency over time with intensity indicated by colors, like warmer colors for stronger signals. It would be a clean and informative representation of the data, easy to understand without any unnecessary details.
So what the screen, what's the web application will look like?
The web application would have a clean main display area for the spectrogram, probably on a dark background for better contrast. Around it, you'd have some control panels or sidebars where you can upload data, adjust the display settings, and maybe select different analysis options. It should be user-friendly with clear buttons and menus.
Yeah, user friendly is nice, but we're not doing uploading. We're not uploading any data. We are happy to start with synthetic data.
Okay, so instead of an upload feature, the application could generate synthetic data directly. There could be controls for adjusting the parameters of this synthetic data, like the type of signal, frequency range, and noise levels. This would allow for users to see how different data characteristics appear on the spectrogram without needing external data files.
Okay, can you review the thought process from the developer?
Sure. Initially, the developer was focused on a complex 3D visualization of biomedical data. Then, based on the feedback to make it more realistic, they shifted to a simpler 2D spectrogram for time series data. They also moved from focusing on external data uploads to generating synthetic data directly within the application, with user-friendly controls for adjusting parameters. The focus is now on creating an intuitive and interactive experience for visualizing the spectrogram based on synthetic data.
Okay, so are we gonna, so what's the final response? And also, are we gonna have any presets of the data? So we're trying to stick to biomedical. I mean, it's fine to have some other examples, just for, to make it more simple, but we'd like to have like presets. Can you make suggestions?
Based on the revised approach, the final response could describe a user-friendly web application that displays a clear 2D spectrogram generated from synthetic data. The application would have controls for adjusting synthetic data parameters, like signal type, frequency range, and noise levels. It would include preset options for typical biomedical signals, like EEG's patterns for brain activity or ECG readings for heart rhythms, as well as basic signals like sine waves or chirps for educational purposes. The interface would provide real-time feedback, allowing users to see how different parameters affect the spectrogram instantly.
Okay, can we add other types of signals like PPG, OCG, things like that? Can you make a longer list?
Absolutely. We can include presets for various biomedical signals. In addition to EEG and ECG, we can add PPG data for blood pressure monitoring and other relevant signals. This would provide a more comprehensive range of options for users to explore different types of biomedical data.
Okay, can you ask the developer agent to generate a comprehensive list, like a drop-down list of data signals that we could be simulating?
Sure, I can ask the
Keep going.
developer agent to generate a comprehensive list of simulated data signals that can be included in the drop-down menu. This list should incorporate various biomedical signals like EEG, ECG, and PPG, as well as other types of signals for educational purposes. I'll make sure to include a diverse range of options to enhance the application's functionality and user experience.
Okay, so the thing is, we want the same type of parameters. So we want like standard signal, time series signal generation parameters to be controllable, and then we want presets. So can you explain it properly?
Got it. You want the app.
Keep going.
To have standard signal generation parameters that users can control, along with presets for specific types of signals. This way, users can both customize the parameters and easily select predefined signals from a drop-down menu. It combines the flexibility of manual control with the convenience of presets.
Okay, can you review the response from the developer? Hey, can you review this response from the developer?
Sure, I can review the response from the developer. Please provide the response so I can analyze it and provide my feedback.
It's on the screen.
Okay, I've reviewed the response. It mentions a drop-down menu with preset signals like EEG, ECG, and PPG, and control parameters for signals like sine waves. However, it doesn't explicitly state that the same parameters can be used for all simulated signals, which was a key point you wanted. We can ask the developer to clarify that the control parameters apply consistently across all simulated signal types, including the presets.
Okay, can you review the developer's thinking?
The developer's thinking seems to be focused on clarifying the interaction between presets and manual controls. They understand the need for consistent application of parameters across all signal types. Their approach is to revise the description to emphasize that presets are starting points that can be customized with granular controls for frequency, amplitude, and noise. This indicates a clear understanding of the user's request and a plan to provide a more precise description.
Okay, what else the developer is saying?
The revised response clarifies that selecting a preset populates the control panel with its parameters, allowing users to then customize them. This ensures a consistent user experience. It also explicitly states that the control parameters like amplitude, frequency, and phase apply consistently across all simulated signal types, addressing your previous concern. The developer also explained that presets are essentially starting points that users can modify, providing a balance between convenience and customization.
Okay, so can you explain how are we gonna go about different types of signals having different parameters?
The application will use a unified control panel, but will dynamically adjust the specific parameters displayed based on the selected signal type. For example, when selecting a sign.
We lost the prompt engineer. We lost the prompt engineer. Let's try a bit different parameters. Okay, so we have this experienced developer that we're talking to. You're going to be acting as a prompt engineer. Hey, can you review the response real quick?
You'd like me to review the response as if I were a prompt engineer providing
that's
feedback
right.
to an experienced developer? I can definitely do that. What aspects of the response would you like me to focus on?
Just review the response.
Okay, I understand. I'll review the response and provide feedback as if I were a prompt engineer. I'll look for clarity, conciseness, and any suggestions to improve the prompt's effectiveness in guiding the development.
Can you cut the fluff and just answer the questions?
Ah, I see. You'd like me to be more direct and concise in my feedback. My apologies. I'll focus on providing direct answers and specific suggestions for improvement without any unnecessary elaboration.
Can you review the text on the screen?
The text describes a unified control panel that dynamically adjusts parameters based on the selected signal type. It highlights the clarity and user-friendly interface. The example mentions a specific signal type and the corresponding adjustable parameters. It also touches on the user's ability to configure parameters for different signal types and the system's ability to generate custom prompts. Overall, the response describes a user-friendly interface with dynamic parameter adjustments and customizable prompts.
Okay, we need the developer to write the full standalone single-shot prompt for the entire web application. How would you ask for that?
I would ask the developer to write a comprehensive, standalone, single-shot prompt that encompasses the entirety of the web application. The prompt should be clear, concise, and provide all the necessary information to guide the application's functionality effectively.
So I was asking to not include any code. That should be fine.
Understood. I will instruct the developer to write a comprehensive, standalone, single-shot prompt.
Now the developer is already working on it. Can you review the developer's thinking process?
The developer is refining the synthesis of the discussed details into a cohesive narrative, pairing it with real-time spectrogram visualization. They are detailing the user experience, focusing on an intuitive interface with dynamic control panels. They are also ensuring a full list of signal types and corresponding controls are included, along with a clear description of the prompt. The developer is aiming for a complete and standalone prompt that covers all aspects of the application.
Okay, what else the developer is saying?
The developer mentioned they have completed a thoroughly refined prompt that captures the core design elements, incorporating the web application logic, visual spectrum data, dynamic control panel functionality, and the comprehensive list of signal types. They believe the prompt is complete and well-structured, accurately capturing the intended design.
Okay, and what do you think about this single shot prompt?
The single-shot prompt seems comprehensive and well-structured. It covers the key aspects of the application, including the interactive spectrogram display, dynamic control panel, and the customizable prompts. The descriptions are clear and detailed, providing a good understanding of the application's functionality. It appears to be a well-composed prompt that should effectively guide the application.
Yeah, what's the response from the developer? Can you review?
The developer is outlining their process, mentioning they've structured the HTML, are working on the control panel, and have defined the data visualization flow. They are also finalizing the signal generation functions and planning the data flow. They aim to create a real-time 2D spectrogram application with various signal types and a dynamic control panel for immediate feedback.
Okay, can you review the web application?
The web application appears to be an interactive spectrogram generator. It allows users to select different signal types like sine waves or EEG and adjust parameters like frequency and amplitude. The application also includes a global noise level slider and displays the spectrogram in real time. It seems to be a useful tool for understanding signal patterns. it seems the drop-down menu allows you to select different types of signals, including sine waves, pulse trains, and even simulated EEG signals with different wave types, like alpha, beta, delta, and theta. You can also adjust parameters like frequency, amplitude, and global noise to see how they affect the spectrogram.
Okay, how would you add an interactive play demo mode to the application?
The overall application is an interactive spectrogram generator. It allows you to generate various types of synthetic signals, including simple sine waves and more complex biomedical signals like ECG and EEG. You can interact with the signal parameters in real time and see how those changes instantly affect the visual spectrogram. It's designed to be an educational tool to help people understand how signals are represented visually.
Okay, didn't get it. We want to include an interactive web simulation for the web application. How would you go about it? So we want a play button on the web application on the interface that will just go through the different parameters, select the different wave type from the drop down and change parameters all by itself.
Ah, I understand. You'd like to add an automated playback feature that rifles through different signal types and parameter values automatically, instead of requiring manual adjustments. This would create a dynamic web simulation where the spectrogram changes on its own, controlled by the parameters in the drop-down menu and the sliders for frequency, amplitude, and noise. Implementing this would likely involve adding a script that loops through different signal types and parameter values, updating the inputs, and refreshing the spectrogram display.
Okay, and how would you also adjust the simulation so it fits into the screen nicely?
To make the simulation fit the screen nicely, you would likely need to adjust the styling of the application's interface, particularly the container for the spectrogram. You could use CSS to set flexible widths and heights, perhaps using percentages or viewport units, to ensure the spectrogram scales appropriately with different screen sizes. You might also want to implement responsive design techniques to optimize the layout for various devices, ensuring that the controls remain accessible and visually appealing.
Okay, can you explain what is the developer gonna be doing with the code, with the web application?
The developer is currently working on enhancing the web application. They're improving the interface, implementing an automated playback feature that cycles through different signal types and parameters, and ensuring the simulation fits the screen properly with responsive design. They're also adding comments to the code and making sure everything works correctly with the spectrogram display.
Okay, what else? What else are they doing?
They've also implemented an error handling function to ensure the canvas doesn't go out of bounds, and added tooltips for the controls to make the interface more user-friendly. Additionally, they've included update comments in the code to document the changes they've made.
Okay, so now as you can see, animation is only going through the different drop-down menu selections, but we wanted to work a bit differently. We wanted to select a certain animation type from the drop-down and then start changing the parameters one by one to different values. How would you go about this?
To achieve that, the code would need to be remodified so that when a specific signal type is selected from the drop-down menu, the animation then focuses on changing the parameters associated with that specific signal type. Instead of cycling through all the signal types, the script would need to identify the selected signal and then vary the relevant parameters, like frequency and amplitude, within a defined range. This would create a more focused and dynamic animation, tailored to the selected signal.
Okay, and also from the drop-down menu, we currently only have sine wave, chirp signal, pulse train, white noise. That's fine. But then for biomedical signals, yeah, we want to add other types of EEG to include the baseline EEG in different types of brain states. So can we do that?
Yes, absolutely. You can add additional signal types, such as EEG patterns representing different brain states, to the drop-down menu. This would involve adding new options to the drop-down and then implementing the corresponding signal generation and visualization logic for each new type. This would allow users to explore a wider range of biomedical signals.
Hey, can we actually do something else? So from the drop down, when we select the EEG, we just want the extra values. So we just have the EEG selection, and then we'll have a control of fine-tuning the waves, so delta, theta, alpha, beta, and including artifacts, added artifacts as well. Can we do that? How would you go about it?
Yes, you can definitely customize it that way. When the user selects EEG from the dropdown, you can then display specific controls for fine-tuning EEG parameters, such as the different brainwave types like delta, theta, alpha, and beta. You can also include controls for simulated artifacts. This will provide a more precise and tailored experience for analyzing EEG data.
Also, currently the animation is only animating, so I'm manually selecting the signal type and then the animation is just varying the parameters within that signal type. So we want to do that for about 10-15 seconds, and then move on to the next signal type. How would you go about it?
You can set up the automation so that the user selects the initial signal type, like EEG. Then, the animation will start varying the specific parameters within that signal type for a set duration, like 10 to 15 seconds. After that time, the user can manually select the next signal type, and the animation will continue with its parameters. This allows for both manual control and dynamic animation within each type.
Yeah, I'll get the notebook LM going as well, because I'm losing my voice.
Okay, I understand. You want to create an interactive spectrogram generator where the user selects the signal type and the system then dynamically varies the parameters within that type for a short duration, allowing for manual switching between types. I can definitely help you with that. You can structure the code to have event listeners for the drop-down selection and use a timer to control the parameter variations within each type.
Okay, we want the animation to be like smoother. So when we're selecting, say, EEG signal, then we're going, for example, no noise. So we're going stage by stage. We're selecting like the delta, increasing the amplitude, varying the global noise level, then setting the parameters back to normal, then going to the next frequency type. So a frequency bands of theta, then selecting a thing, doing the same, varying the amplitude and going next, like in a specific order, not just randomly, not just purely random. How would you go about it?
Ah, I understand. You want a systematic approach where the animation transitions smoothly between different brainwave types and adjusts the amplitude and global noise levels sequentially. To do that, you'd need to create a script that sets the parameters step by step for each brainwave type, adjusting the amplitude and noise levels before moving to the next frequency band. This way, the animation will transition smoothly and follow a predefined sequence rather than being random.
Okay, can you go over the logic from the developer? I think we lost the prompt engineer again, did we? Yes. Yeah, we can't get hold of a prompt engineer. Okay, let's do this review. I'll probably finish unless so there is a human in the loop. If you have any questions, go for it. Go check out the website. We have tools like advanced EEG signal simulators. Go test it out. Let me know what you think.
Welcome back to the deep dive. We're digging into something that sounds, well, pretty technical today. It's called an interactive spectrogram generator with signal simulation. Basically, a way to make and see data patterns. Sounds straightforward, maybe a bit dry. But yeah, there's something else going on here. It's surprisingly weird. Okay, so first off, the range of signals this thing can generate is pretty wide. You've got the basics, like a sine wave, simple enough. Then there's a chirp signal. That's where the frequency changes, right? Kind of slides up or down.
Yeah, exactly, like a little sweep. And you mentioned the others, too.
Right. A pulse train, just rhythmic bursts. And even white noise, just that static fuzz. And the controls for time and frequency seem, well, incredibly specific. Like you can really dial things in.
Oh, absolutely. That technical side, the precision engineering for making those basic waveforms,
Yeah.
it's genuinely impressive, really clean work. But, like you hinted, that's not the whole story.
Yeah.
It's not just that it makes signals precisely. The really fascinating bit, maybe the slightly unsettling bit, it's what signals it lets you simulate. It goes way beyond just, audio stuff or simple physics demos.
Okay, you're setting a tone here. So it's not just sine waves and noise. What kind of signals are we talking about that makes this feel different?
Well, that's where it gets interesting. You look down the signal type menu, past the sine wave, past the chirp, and suddenly you see options like EEG signal.
EEG, like brain waves?
Brain waves, yeah.
Yeah.
Then ECG, electrocardiogram, your heart's electrical signals.
Okay.
And not just one ECG gives you options. Normal sinus rhythm and ECG arrhythmia.
Wait, arrhythmia, like an irregular heartbeat?
An irregular heartbeat, yeah. And also PPG, the pulse wave, the normal kind at least.
So, hold on. This generator lets you just click a button and simulate a heart arrhythmia the same way you'd click to make, like, white noise?
Essentially, yes. It's just another option on the list. And that's where you get that dark humor, that irony, right?
Right. It's just, wow. The casualness of putting a potentially fatal condition next to, a basic audio tone. It feels jarring.
Exactly. And think about the other controls. It mentions a global noise level parameter.
Okay.
And it's set, like, super precisely at 0.05. That's not just random noise. It's this tiny, controlled amount of fuzz you could add, almost like simulating the imperfections of a real biological system, but with perfect control.
Controlling the chaos, almost.
Sort of, yeah. And then there's the start automation button.
Meaning
you can just set these signals, even the arrhythmia, to just run, generate automatically, precisely, on loop.
But hang on, couldn't that precision actually be, well, really useful? I mean, simulating an arrhythmia accurately, couldn't that be great for, say, training doctors or testing medical devices?
Oh, absolutely. That's the flip side, isn't it? The potential benefit is huge. Imagine medical students learning to spot complex heart problems on a simulator that perfectly replicates the real thing, but safely. That could save lives, no question.
Okay, so it's not just unsettling then.
No, it's both. It holds this incredible potential for good, for training, for research. Perfect simulation can be a powerful tool. But then you think about the other side. What if someone could generate, I don't know, fake medical data that looks perfectly real, or use this kind of precise biological signal generation for, well, less helpful reasons?
Deep fake heartbeats. That's a thought.
It forces you to grapple with what simulation means when you can craft the electrical signature of a heartbeat, or its failure, so perfectly. When you can command something that feels so fundamentally chaotic or vital with such clinical detachment. So maybe the question we leave you, the listener, with is this. In a world where the tools let us generate the signals of life and, well, death, that's the same few clicks, where arrhythmia sits right next to sine wave, what would you choose to simulate? And maybe more importantly, why?
Okay, so got a few improvements to it. So hopefully it will be ready for production sometime soon. I keep losing the prompt engineer. Just use default settings for a sec. Hey, can you overview the thinking from the developer?
The developer is focusing on improving the HTML structure and readability of an interactive spectrogram generator. They've drafted the content for different sections and are now planning to use Tailwind CSS classes to enhance the visual presentation. They'll also integrate these new sections into the HTML code and ensure the application is functional.
And can we ask the developer why the automation button is grayed out? Why is that not working? We don't get any errors in the console. I know, so we see it for the EEG
The automation
signal.
button. The automation button appears to be disabled when the sine wave signal type is selected. It seems to only be enabled when using the EEG signal type, suggesting that the automation feature is specifically for that signal type.
Okay, we would like the automation to be available for other signal types as well.
Got it. The developer should extend the functionality of the automation button to include other signal types, like the sine wave and ECG, by modifying the underlying code that controls the button's state and functionality.
Okay, we can try that. Also, so in the same way, like we have the EEG signal with its unique parameters, we want the ECG to be the same. So in the dropdown, we should just have just the ECG signal, and then the parameters, the different parameters in it.
So you'd like the signal type dropdown to have only the ECG signals as an option? And then the related parameters should be specific to the ECG signal. similar to how the EEG signal currently works. The developer should update the drop-down options and the corresponding parameters based on the...
Yeah, it's really bad. It's really bad. It's the AI Studio. Everything else seems to work really well. ECG. Yeah, currently the automation, it made it only work for the EEG signals, which is a bit unfortunate, but hopefully we can fix that. Yeah, we'll finish the stream on LinkedIn. There's nothing happening there. Let's try and bring the prompt engineer back. Not sure what if any of the parameters make any difference. Let's reduce the tokens, see if it helps. Can you review what the developer have done with this web application real quick?
Okay, I see they've created an interactive spectrogram application. It allows users to generate different signal types, like brainwaves, and visualize their frequency content over time. Users can adjust parameters such as signal type, frequency, amplitude, and noise levels, and see the effects in real time.
Okay, so the developer also removed, we had the other signal types there before, sine wave, chirp, pulse train, white noise. If we can bring them back,
Yes,
that
I see.
would be great. Yeah, that would be great. And also another thing is, yeah, so the animation now works for every drop down, so just varying the parameters that we have, which is good. Yeah, I don't think there's
Understood.
There's also in ECG signals, there's not much a difference between normal sinus rhythm and arrhythmia. So if we can check that, I don't think that's actually working. And in EEG, we want to be able to, in EEG, we want to be able to vary all the bands, all the frequency bands simultaneously. So change the amplitude all at the same time, so we can see all of them potentially on the spectrogram. So can you turn all what we discussed so far into instructions for the developer, questions for the developer? Just keep in mind it's a highly experienced developer, so
Sure. Here are some instructions for the developer. First, please reinstate the previously removed signal types, including sine wave, chirp, pulse train, and white noise. Second, ensure that the animation works properly for all selectable parameters across all signal types. Third, address the issue where there is no discernible difference between normal sinus rhythm and arrhythmia in the ECG signal type. Fourth, for EEG signals, implement the functionality to vary all frequency bands and their amplitudes simultaneously on the spectrogram. And finally, ensure that the changes are seamlessly integrated and the application remains stable.
Wow, that's pretty good. What's the developer's thinking process?
Based on the instructions, the developer seems to be focusing on refining the user experience and expanding the functionality. They're aiming to make the application more intuitive and educational by incorporating smoother animations, restoring the removed signal types, and ensuring the accuracy of the ECG signals. Additionally, they're adding a feature to simultaneously vary EEG bands, enhancing the application's capabilities for analysis.
Okay, what else are they doing? What else the developer is doing at the moment?
It looks like the developer is also updating the code structure and re-implementing the signal generation functions. They're making sure the application remains stable and that all the animations work smoothly with the new signal types. They're also ensuring that default parameters are visually distinct for a better user experience.
Again, can you review the code real quick as well?
Based on the code snippets visible, it looks like the developer is using HTML for the structure, CSS for styling, and likely JavaScript for the interactivity and signal generation. They seem to be using specific elements like sliders and dropdowns for user input. The code appears to be organized, but a more comprehensive review would be needed to assess its efficiency and potential issues.
Okay, there's one problem, as you can tell. What do you think the problem is? It's the Y scale of the frequency.
I see. It looks like the y-axis of the spectrogram, which represents the frequency, isn't displaying the different frequency bands clearly for the brainwave signals. It's not showing the individual delta, theta, alpha, and beta bands distinctly.
I think it is. It's just the scale of the chart.
That makes sense. The developer might need to adjust the scaling of the y-axis on the spectrogram to properly display the different frequency bands for the brainwave signals, making them clearly visible and distinguishable.
Okay, and can we also fix the frequency and time labels on the chart and the axis? Do we need to add axis?
Yes, ensuring that the frequency and time labels on the spectrogram are accurate and clearly displayed is crucial for the user's understanding of the data. The developer should make sure these labels are correctly aligned and easy to read.
Do you think we should have some controls below the spectrogram chart?
Yes, adding controls below the spectrogram could enhance the user experience. This could include options to adjust parameters like the frequency range or time window displayed, or even playback controls for the signal generation. It would make it easier for users to interact with the visualization.
Wait, so we have these controls already under the frequency spectrum chart. Should we just have controls over the scale, the axis, the scale of the axis, but then the web application should automatically pre-select those when changing different signal types and things like that. So can you explain it properly?
Sure, the developers should keep the existing controls below the spectrogram chart, but focus on enhancing the control over the scaling of the y-axis to ensure the frequency bands are clearly visible. Additionally, the web application should automatically suggest the optimal scaling for the y-axis based on the selected signal type and parameters, providing a seamless and intuitive user experience.
Okay, it's actually pretty good. It's pretty good as is.
Great! So it sounds like the core functionality is working well, and the suggested changes will further improve the application's usability and clarity.
Yeah, so the X, Y are good, but yes, we would like to make them better. We'd like to fix the. We'd like having some controls on definition. So, for example, log scale, not log scale, switch below the spectrogram chart, and also the range, which will be indicating what's automatically is being selected by the web application, by the algorithm. Did you get that? Yeah, I'm having issues with the. Anyway, I really like this web app. It's really nice. It's really nice. We lost the prompt engineer. We lost the prompt engineer. That's not fun. Yeah, I'm not sure how accurate the eye blink is. It's varying it randomly, which is nice. Which is nice. Can you quickly explain what do you see on the screen?
I see a tool called the Interactive Spectrogram Generator. It looks like it's used to visualize EEG signals, probably for brainwave analysis. You can adjust different settings, like the signal type and frequency bands, and see the spectrogram change in real time.
Okay, that's nice. Now for the EEG, for example, what's the problem with the chart, particularly the Y and X axis?
The y-axis in the spectrogram represents frequency, and the problem is that it's currently displayed on a linear scale. This makes it difficult to see the lower frequency bands, which are often important for EEG analysis. The x-axis represents time, and it could be improved by adding more detailed labels and better dynamic updates.
Wait a sec, can you double check, is the frequency linear or logarithmic scale at the moment?
It's currently on a linear scale, and the suggestion is to switch it to a logarithmic scale.
It's logarithmic scale at the moment, can you double check?
Apologies for the mistake. You're right. The frequency axis is currently on a logarithmic scale. The suggestion was to use a logarithmic scale, which it appears to beacon already.
Okay, how would you improve the axis and the display? And we would like controls under the spectrum chart that will indicate the current settings. So the range of X and Y, and if it's logarithmic or linear.
To improve the display, you could add controls below the spectrogram to indicate the current settings, such as the frequency range and the scale used, logarithmic or linear, for the y-axis, as well as the time span displayed on the x-axis. This would make it clearer for users to understand the visualization.
Okay, but also can we make sure that those controls are varied automatically by the algorithm, depending on which signal type is selected?
Yes, you can design the controls to automatically adjust their values based on the selected signal type. For example, when EEG signal is selected, the frequency range can automatically be set to typical EEG bands, and the scale can be set to logarithmic. If a different signal type is chosen, the controls can display the appropriate range and scale, automatically.
And how do we make sure that the y-x axis, the number on the axis and the label of the axis look correct, appear correctly?
To ensure the axis labels and numbers appear correctly, you can use dynamic label generation in your code. This way, the labels and tick marks will be updated automatically based on the selected signal type, frequency range, and time span. You can also use formatting techniques to make the labels readable and prevent overcrowding on the axes.
And currently we have general signals. Then within biomedical signals we have EEG, two types of ECG, PPG. What other signals would you recommend adding?
Besides EEG, ECG, and PPG, You could add signals like EMG for muscle activity or EOG for eye movements. These are common signals used in biomedical research and could provide a more comprehensive analysis in your tool.
Also, within the ECG, so in the dropdown, we currently have both ECG normal and ECG arrhythmia. Do we need can we have the abnormal ECG to be, so in the signal type dropdown, only have ECG, and then within that, the control should then have an option to select between normal and abnormal ECGs. Can you explain that properly?
Yes, that's a good idea to consolidate the ECG signals. You could have a single ECG selection in the signal type dropdown, and then add separate control, perhaps a radio button or another dropdown, below to specify whether it's normal or abnormal ECG. This would make the interface more organized and intuitive for users. To improve the spectrogram display, you can ensure the labels for the y-axis and x-axis are clearly positioned and formatted for readability. For the y-axis, make sure the logarithmic scale labels are spaced appropriately and consider adding grid lines to help with interpretation. For the x-axis, ensure the time labels are dynamic and reflect the current time span. Additionally, you can add clear indicators below the spectrogram to show the current frequency range, axis scale, logarithmic or linear, and time span. This will provide more context and make the visualization easier to understand. The developer is currently implementing enhancements to the EEG spectrogram based on the suggestions. They've added a new ECG signal type and included a separate control for selecting between normal and abnormal ECG. They've also incorporated dynamic labels for the axes and are working on adding controls to display the current frequency range, axis scale, and time span. The developer is also working on improving the visual clarity of the spectrogram by adding grid lines to the axes. They are also planning to add biomedical signal types, such as EMG and EOG, to expand the functionality of the tool. Sure. Looking at the code, I can see the implementation of the new signal type options, including the consolidated ECG selection and the separate control for normal and abnormal ECG. The code also includes the logic for dynamic label generation for the axes and the controls to display the current settings below the spectrogram. It looks like the developer is implementing the suggested improvements. Yes, you can adjust the frequency range displayed on the y-axis to be more appropriate for each signal type. For EEG, you can set the range to typical brainwave frequencies. And for other signals like ECG and PPG, you can define the relevant frequency bands to ensure the spectrogram is informative and easy to read. This will make the visualization more accurate and user-friendly. To further improve the tool, you could consider adding features like the ability to zoom in and out of the spectrogram or pan across the time axis for more detailed analysis. Additionally, adding options to customize the color palette and display settings could enhance the user experience. Another valuable improvement would be to allow users to export the spectrogram as an image or the underlying data for further analysis. Also, incorporating tooltips that display detailed information when hovering over the spectrogram could enhance the user's understanding. To improve the page layout, you could rearrange the elements to make better use of the space. You could place the controls for the signal type, frequency range, and other settings beside the spectrogram instead of above it, and make the spectrogram larger to fill more of the screen. You could also consider collapsing some of the control sections to reduce clutter. Yes, I see what you mean. The spectrogram for EEG signals appears to have too much empty space, especially in the higher frequency range. This indicates that the y-axis scaling might not be adjusting properly to the specific signal type. To fix this, the scaling should be optimized to focus on the relevant frequency range for each signal, ensuring the spectrogram utilizes the available space effectively and displays the important data clearly. You're I see now. The spectrogram is only showing a small portion of the frequency range, even when the y-axis scale is set to logarithmic. It seems like there might be an issue with how the data is being mapped to the display, causing the spectrogram to only show a limited frequency band. This needs to be corrected to ensure the entire relevant frequency range is visible. You're You're absolutely right. When selecting the sine wave, the spectrogram displays the frequencies correctly, but for EEG signals, it's not displaying the full frequency range. This suggests there's an issue with the data mapping specifically for EEG signals, which needs to be corrected to show the complete frequency spectrum. Yes, it does appear that there's some code cleanup needed to ensure the spectrogram functions correctly for all signal types. Specifically, the code related to the y-axis scaling and data mapping for EEG signals should be reviewed and corrected. Additionally, ensuring consistent behavior for all signal types will improve the overall reliability of the spectrogram. Yes, that's possible. When scaling the y-axis, particularly with a logarithmic scale, it can affect the resolution displayed. If the scaling is not handled properly, it could lead to a loss of detail or distortion in the frequency representation, making it difficult to see finer details of the data. It's important to ensure that the scaling axis preserves the resolution while providing a clear and informative display.
We lost the prompt engineer. Sorry, my microphone was muted. Muted. Okay, we need to fix this somehow so the animations seem to work. Animations seem to work correct. EG signal, yeah. What's up? Hey, let's see. Can it fix it? Let's try calling the prompt engineer again. Can you explain the response from the developer?
The developer has made several improvements to the visualization. They've increased the frequency resolution, corrected the y-axis scaling, added new color palette options, enhanced axis labels and grids, refined the arrhythmia generation, and cleaned up the code. These changes aim to make the spectrogram clearer and easier to interpret.
Wow, that will be a lot. Do you think the code will actually work? Can you review the code real quick?
From what I see, the code looks pretty well structured. It includes the necessary HTML elements for the controls in the spectrogram display, and the CSS appears to handle the styling. The JavaScript part, although not fully visible, seems to implement the functionality for the dynamic controls in the spectrogram generation. It looks like it should work based on what I can see.
Well, fingers crossed.
I'm optimistic it will work well. The developer seems to have addressed the feedback thoroughly, and the code structure looks promising. Let me know if you encounter any issues when you test it.
Well, they're still developing the code. Maybe you can do a quick review of the code.
Sure. Based on the code I can see, the developer has implemented the signal generation functions and the FFT implementation. It looks like they're working on the dynamic controls in the spectrogram display. The structure seems sound, and they appear to be addressing the feedback points effectively. It's looking like it should work well.
Okay, so we have the code working. Yeah, it seemed to be, well, linear, logarithmic. Yeah, so now we have more high resolution on the frequency on the y-axis.
Yes, the developer has successfully increased. That enhanced frequency resolution provides a much clearer view of the frequency content, making the spectrogram more detailed.
Okay, we have 773 lines of code. Okay, let's test it real quick. There's still a lot of empty space, so when I'm selecting EEG, why all the empty space below the spectrogram?
The empty space below the spectrogram is likely reserved for the dynamic controls that will appear when you select a specific signal type, such as EEG. These controls will allow you to adjust parameters for the selected signal.
No, I'm talking about the space between the bottom of the spectrogram and the x-axis, the time axis.
Ah, I understand. That empty space might be due to the way the y-axis scaling is implemented, especially with the logarithmic scale. It's possible the scaling adjustments are affecting the layout of the spectrogram. The developer might need to fine-tune the scaling parameters to optimize the display area.
So can you explain what the problem might be?
The issue might be that the logarithmic scaling is not fully utilizing the available vertical space. Logarithmic scales tend to compress lower frequencies, which can leave empty space at the bottom of the spectrogram if the scaling parameters are not optimized for the specific frequency range being displayed. Adjusting the scaling parameters or the y-axis limits could help to utilize the space more effectively.
Okay, and also how about the space between the time x-axis and the controls of the spectrogram at the bottom of that section?
That space might be part of the layout and design of the application. It's likely intentional to provide some visual separation between the spectrogram display and the controls below it.
Now that's too much space. Can you explain what the problem might be?
Well, it might be a design choice by the developer to create a clear separation between the spectrogram visualization and the control elements. However, if it appears excessively large, it could be due to specific layout settings or the use of padding or margins in the user interface design. Adjusting those spacing properties could reduce the gap to make the layout more compact.
Okay, let's see if that helps. Can you give an overview of what is it we are trying to do?
We are trying to optimize the visual representation of the interactive spectrogram generator. The main points are to improve the frequency resolution, adjust the y-axis scaling for better visualization, enhance the color palette options, make the axis labels and grids clearer, refine the signal definitions, and address the spacing between the spectrogram and the controls. The overall goal is to make the application more accurate, clear, and user-friendly.
And what's the developer's response at the moment?
The developer acknowledges the feedback regarding the logarithmic scaling and layout spacing. They plan to correct the logarithmic scaling logic, increase the frequency resolution, adjust the padding and margins for a more compact layout, and enhance the grid lines to improve the spectrogram display. They are also updating the code in Canvas based on these changes.
So does it look like the user is able to change so currently the user is able to change the type of y-axis from linear to logarithmic and the color map, but are we able to change the range of the frequency and the time window?
Based on the current view, it looks like the user is not able to directly change the frequency range and time window from the visible controls. The controls available are for the signal type, y-axis scaling, and color map. The frequency and time values might be predetermined or adjustable through other settings not visible in this view.
Okay, and should we be able to control the frequency and the time range? What do you think?
Yes, it would be beneficial to have the ability to control the frequency range and time window. This would allow users to focus on specific frequency bands of the signal or analyze different time periods, making the spectrogram generator more versatile and useful for various analyses. It would also enhance the user's ability to explore the data more effectively.
Okay, the developer made all these changes, but there is still too much gap between the bottom of the spectrogram and the time x-axis, and also between the x-axis and the controls at the bottom of that specific group. Papa, we lost the prompt engineer. We lost the prompt engineer. Okay, there still seems to be too much space between the bottom of the spectrogram and the time x-axis. Additionally, there is still too much space, way too much space between the time x-axis and the controls of the spectrogram at the bottom of that same group of elements. Can we make the layout much, much better?
Imagine if you could actually see your brain waves. Or, your heartbeat, maybe even your voice kind of wiggling through the air.
Yeah, not just hear it, but actually watch its invisible dance.
Sounds a bit intense, maybe even a little revealing, doesn't it?
It certainly does. And today we're doing a deep dive into something called an interactive spectrogram generator.
Okay, sounds technical.
It does, but it's actually a tool that gives this surprisingly intuitive shortcut to understanding that hidden world of signals.
Right, so our mission today is to pull out the really fascinating bits from this educational tool, see how it turns abstract data into something visual, a story even.
And maybe, just maybe, touch on a few darker, more humorous aspects of being human along the way.
All drawn from the source, excerpts from Interactive Spectrogram Generator, signal analysis tool.
Exactly. So first off, what is a spectrogram? It's basically this powerful way to visualize the frequency content of a signal.
Okay.
Think sound, biological data, anything really. And crucially, how those frequencies change over time.
So it makes the unseen sort of visible, like a dynamic map.
Precisely. A dynamic, often color-coded map. And what's neat about this generator is it's real-time, interactive, and it uses synthetically generated data.
Meaning
You get this hands-on learning experience without needing, fancy lab equipment or real biological sensors.
Yeah.
It's designed as an educational resource.
accessible. Lets you just jump in and play with signals to understand signal processing basics.
Yeah, you can literally play with signals.
Yeah.
Which brings us to a pretty intriguing part, the EEG signal controls.
Ah, the brainwaves.
Right. Imagine having sliders to tweak your own simulated brainwaves. You can independently adjust the amplitude for delta waves.
That's deep sleep, right? 1 to 4 hertz?
Yep. And theta, which is
Yeah.
sort of drowsy, 4-8 hertz. Then alpha, that's your calm, awake state, 8-12 hertz. And beta, for active thinking, 13-30 hertz.
Okay, so having direct control like that, it feels a bit like playing God, doesn't it? What happens if you just crank up the beta waves? The example has beta amp at 0.9, pretty high.
Well, yeah, simulating that hyper-alertness, maybe even anxiety, it really forces you to see how tiny changes in these signals could relate to, well, massive shifts in our internal state. It teaches you that relationship directly.
Or maybe trying to silence your inner monologue by dialing alpha down.
It makes you think, definitely. And then there's the flip side, the noise. The tool mentions artifact type, though it's none in the example,
Okay.
but also global noise level. In the example, it's 0.88, which is actually quite significant.
So it shows how easily real signals get messy.
Exactly. How noise can just obscure the features you're looking for. It's kind of a digital echo of our own noisy internal landscapes, right? Constant distractions.
A very apt comparison, so it's not just brain activity, it simulates.
Oh, no, not at all. It handles other signals too, like ECG, the heart's electrical activity. You can switch between a normal rhythm and an erratic arrhythmia.
Visually showing health versus dysfunction. That's powerful.
It is. And also PPG, photoplethysmogram, which relates to blood volume changes, shows its versatility.
And what about how it's displayed? Does that help understanding?
Absolutely. There are display settings like using a logarithmic y-axis.
Why logarithmic?
Well, it's particularly useful for distinguishing those low-frequency components, like the different EEG bands we talked about. It spreads them out visually.
Makes sense. Otherwise, they'd be squished at the bottom.
Right. And then there's the automation feature.
Yeah.
For the truly let's say, efficient learner.
Ah, efficient. You mean lazy.
Maybe. Dynamically animates the parameters for you, so you can just sit back and watch how things change without touching the sliders yourself. The tool that teaches you even while you nap.
Love it. Okay, looking ahead, the future directions sound pretty interesting. Complex signal mixing, like combining an alpha wave with 50 hertz power line noise.
Yeah, think about that. It's almost a metaphor for modern life, isn't it?
How so?
Your peaceful alpha state, your calm focus, constantly getting buzzed by this background hum, this interference.
It's like trying to meditate next to a construction site.
Pretty much. It teaches you about signal contamination, why filtering is so important.
And what about real-time audio input? Processing your own voice from a microphone.
Ooh, now that's provocative.
Right. Imagine seeing the raw, unfiltered visual truth of your own voice. Would you like what you see? Would karaoke night ever be the same?
It's a confronting idea, for sure. Seeing your own vocal fingerprint laid bare.
Then there's the more technical stuff mentioned. Advanced STFT controls, FFT size, windowing functions like hamming, black man.
Yeah, that points toward the sophisticated math behind it all, the techniques needed to fine-tune the analysis for different purposes.
And finally, data export. Saving the spectrogram as an image or the raw data as like CSV or WAV files.
Which leads to the ultimate self-tracking possibility, doesn't it?
Archiving every last twitch and hum of your existence for, I don't know, future analysis. Or maybe just digital hoarding.
Could be. It taps into that obsession.
So wrapping this up then, what's the core takeaway from this deep dive, this interactive spectrogram generator? It seems like more than just code.
Definitely. It's a really insightful tool. It makes the invisible world of signals visible, understandable. It helps you grasp these fundamental ideas of signal processing by letting you actually see the hidden dynamics. Brainwaves, heartbeats, sound.
It turns abstract concepts into something you can interact with.
Precisely.
Which leaves us with a final thought for you, the listener. If you could visually dissect every little signal inside you, or even just the sounds around you every day.
Yeah, what would you truly learn? What profound insights, or maybe what uncomfortable truths might surface?
And perhaps more pointedly, what parts, once you'd seen them visualized, would you wish you could just unsee? Or maybe unhear?
What if you could actually, see a heartbeat,
Mm-hmm.
or maybe a thought flickering, or just pure chaos happening right there on your screen? Today, we're diving into something pretty cool, the interactive spectrogram generator. It's this really powerful tool that helps make invisible signals suddenly very, very visible.
Exactly. It's all about seeing the frequencies inside a signal, how they change over time. Basically, it's hidden tune, you could say. And the really neat part, it makes up all this data itself synthetically right in your browser so you can just jump in and play around.
No complex setup needed.
Nope, none at all. It's like a sandbox, really. A safe place to poke at data analysis.
Okay, so you mentioned playing around. Let's talk signal parameters.
Yeah.
What kinds of signals can we actually generate here? Beyond the obvious ones, maybe.
Yeah, you start with the basics, like a sine wave. That's your pure single frequency. Think of it like a perfect musical note, unchanging.
Gotcha. The simplest building block.
Right. Then you've got chirp signals. These are fun because the frequency changes over time. It sweeps up or down.
Oh, like radar or sonar does?
Correct.
Or maybe a bird call?
Exactly like that. Bats use something similar too. And then there's white noise.
Stat.
Pure random static, yeah. Contains all frequencies equally. It's, essential for understanding randomness and, well, noise itself.
And this is where it gets really wild for me. It simulates biomedical signals.
It does. You can generate things that look like EEG signals, that's brain activity,
Wow.
or ECG, the heart's electrical rhythm, EMG for muscle activity, EOG for eye movements, even PPG, which is often used in pulse oximeters.
So you can sort of see your brain working or your heart beating without any actual, messy biology involved.
Precisely. It's a simulation, but it visually mimics those patterns really well. It lets you see the structure.
But just seeing the signal isn't enough, is it? How do you, tweak the view? Choose your lens, so to speak.
Good question. That's where the display settings are key. You can adjust the max frequency shown.
So zoom in on a specific frequency range.
Exactly. Or change the time window, see a longer stretch of time, or focus on a shorter moment. And crucially, the y-axis scale. You can pick logarithmic, which is great when you have huge variations in power, or signals that change exponentially.
Okay.
Or just linear for a straightforward comparison. And don't forget the color map. Viridis, Inferno, Plasma, Grayscale.
Does the color really make that much difference?
Oh, absolutely. Different maps highlight different intensity levels or patterns. It genuinely changes how you interpret what you're seeing. It's not just cosmetic.
Okay. Now, my favorite part, potentially, the slightly dark humor bit. You've got your perfect signal, you've tweaked the display, and then there's this slider for global noise level. You can just add chaos.
You can just inject pure statistical chaos, yes. It's almost comical how well it works.
Right, you dial it up, and that beautiful clear signal you had.
Poof! It can get completely buried. It's like a digital dimmer switch for clarity run by gremlins.
But there's a serious point here, isn't there?
Oh, definitely. It's critical. Because in the real world, noise isn't usually something you add with a slider. It's just there, always.
It's unavoidable.
Exactly. So this feature, it's a fantastic, maybe slightly sobering lesson in data integrity. It forces you to ask, what am I really seeing here? Is that a real feature, or is it just noise?
Or maybe something someone wants hidden by noise.
That too. It's about critical thinking when you look at any data, really. What's signal, what's noise, what might be deliberately obscured.
So looking ahead, what's next for a tool like this? Any future directions mentioned?
Yeah, some exciting ideas like complex signal mixing. Imagine layering different signal types, a sine wave plus some noise plus maybe a chirp. See how they interact.
Ooh, that could get complicated visually, but interesting.
Very, or even real-time audio input, using your computer's microphone to feed sound directly into the spectrogram.
Whoa, so you could literally see the frequencies in your own voice or music as it happens.
Potentially, yeah. That opens up a whole world of real-time exploration, understanding the world through its vibrations, essentially.
It really is an amazing way to get a shortcut, isn't it? To understand hidden data, see the structures underneath.
It absolutely is. It gives you a kind of fluency in this secret language of signals. A powerful lens.
A peek behind reality's curtain, maybe. See the invisible stuff.
Yeah, but it also leaves you with a thought, doesn't it?
Oh.
Well, if we can take a perfectly clean generated signal right here and deliberately bury it in noise with just a slider, how much unintentional or intentional noise are we wading through every single day in the news we read, the data we see online? What signals, what crucial information might we be missing entirely just because we don't have the right tools or maybe the right critical filters to see past all that noise? Something to think about. Okay, so let's dive in today. We're looking at something pretty interesting, an interactive spectrogram generator. Imagine like having a window, a personal window into this whole unseen world of signals where all this complex data, it just sort of transforms into these quite mesmerizing visuals. It gives you this instant clarity really on how things like, I don't know, a simple musical tone or even the electrical rhythms in your own body actually look, how they behave over time. And our mission, I suppose, is to unpack how this tool, and it runs right in your browser, makes some pretty sophisticated signal analysis, well, frankly, surprisingly accessible and kind of fun, actually. It's not just about looking at nice patterns, though. You need to think critically to figure out what you're seeing. The irony, which I quite enjoy, is that you finally get to see stuff that's normally totally invisible.
Exactly. And what's really insightful, I think, is how it demystifies the spectrogram itself, which, is a super powerful way to visualize how a signal's frequency content changes over time. By generating synthetic data right there, in the browser, this tool just cuts through a lot of the usual barriers. No messing with external files, no complex setups needed. It's really set up as an educational thing, to help you grasp these fundamental ideas in signal processing.
Right. And it's not just showing you like basic waves either. You can play around with standard signals, sure, like a pure sine wave or a chirp signal. That's the one that sweeps its frequency, right? Crucial for things like sonar. You see its frequency just steadily changing on the plot. Then there's white noise, which is just, well, delightfully chaotic. And watching that on a spectrogram, it immediately shows how a truly random signal just splashes its energy everywhere across all frequencies.
Yeah, totally random.
But then it gets, I think, critically interesting when you switch to biomedical signals. Things like EEG for brain activity or ECG for heart rhythms, even EMG for muscle signals, or EOG for eye movements. Seeing these visualized directly, it can offer some pretty startling understanding, I think, into these really complex real-world data streams.
It really can. And if you think about the bigger picture, it highlights just how much vital information is flowing around us, often completely unseen, unheard. That control section in the tool, it's not just a set of sliders. It's where you actually get to sort of manipulate this invisible world. So adjusting the max frequency, for example, lets you zoom in spectrally, right? Focus on specific frequency bands, maybe reveal components that were hidden before. Yeah, refine the view. And changing the time window helps you either catch really brief events, transient things, or look at longer-term patterns. It really forces you to think, okay, what subtle dynamics might we be missing if we couldn't visualize things as precisely?
And then there's my favorite part, the almost darkly humorous bit, the global noise slider.
Ah, yes, the chaos control.
Right. There's something just ironically perfect about having a specific control to deliberately, mess up your nice, clean signal.
It is a bit cheeky, yeah.
It just applies random noise across whatever signal you've generated. And what's fascinating is how instantly it shows you the brutal reality of real-world data.
Mm-hmm. It really does.
It just lays bare how easily noise can just swamp the important features in a spectrogram. Shows you exactly why things like sophisticated noise reduction techniques are so absolutely essential in fields like, say, medical diagnostics or comms.
Absolutely.
You can even automate the parameters, turn everything on, and it feels like you're watching some kind of, alien symphony of chaos conducting itself. It's quite something.
It's a powerful lesson, isn't it?
Mm.
Makes you critically look at not just the signal, but the way it's being shown to you. The different color map options, for instance, Veritas, Inferno, Plasma, Grayscale. They aren't just there to look pretty.
Right, they actually matter.
They absolutely do. They can literally reveal or hide certain details. What might be a really subtle peak in one color scheme could become glaringly obvious in another. And this reinforces the real value of a tool like this. It's not just about passively seeing data. It's about actively understanding how your display choices, your settings, impact what you perceive and what you can analyze. It makes you question the presentation, not just the data itself.
That's the real power, I think. This kind of real-time visualization, even if it's in a simulated space like this, it just opens doors to understanding data in so many fields. Makes you wonder, doesn't it, how many layers of hidden information are constantly swirling around us all the time? So, thinking about that. If you, listening, could visualize any unseen signal from your daily life, maybe the subtle hum from your fridge or the unseen tension in a difficult conversation, perhaps even the flow of abstract ideas, what would you choose? And what surprising insights do you think seeing it laid out like that might actually reveal? Something to ponder.
So this will eventually be available on BioniChaos.com. Go check it out. Provide your feedback, what you like, what you dislike. You don't like the colors.